Welcome! In this session we're going to learn how expired eggs behave differently from fresh eggs when placed in water, and then we will try to explain this scientifically, and this trick is going to help us in future to know how we can test our eggs in order to make sure if they're still usable or not. So I'm going to ask you to be attentive and listen to what's going to happen.
Hi, it is a pleasure of mine seeing you guys around today. Today we want to be talking about our eggs here, right? So actually I have normal eggs, the one that we use in our homes, the one that we use in our shops, whatever. So and then we need to know which ones still in good condition, which one's still fresh, and then which one are expired. Okay. So this is a good trick for you to know if your eggs still fresh or are expired. But what you're gonna do is I'm gonna try to put them in water so you can see what's gonna happen, and then after that I'm gonna try to demonstrate it mathematically what's happening for it to be doing what it's doing. So let's go. I have 5 eggs. Okay. Then I'm gonna put them in this normal water in my tank. This is normal water that you can find from a tap, with normal temperature, There we go. So realize that 3 of my eggs are touching the bottom of my tank, and then 2 of them are on the surface of the water, so they're kind of floating. Okay. So now I'm going to try to demonstrate to you why this is happening mathematically. Okay. So let's go. A normal fresh egg has a density, okay, of 1.031 gram per centimeter cube. Agree with me? And this water here that is for a normal egg, a fresh egg, and then this water here has a density of 0.997 gram per centimeter cube, or I can just say 1 gram per centimeter cube. Okay. And then we all know that if you want to get a density, what you do is you take the mass of the egg. These are normal size, like average size eggs. So I can say they are between 5 to 65 grams. Okay, according to how they look like. And then so what you do is, for you to get a density, you take the mass of your egg, you divide the mass, you divide it by the volume. Okay, so this egg is an elliptic shape.
We know that the volume of an egg is given by
taking 4 divided by 3, multiplying by the transversal size or transversal dimension, which I've named B, and then multiply it by the tangential size, which I've named A, and then multiply by the longitudinal size, which I've named C, and then this multiplied by pi. So this is how you
get the volume of your ellipse.
So our eggs have elliptic shape. So now let's go. So why are those ones floating? Why are those at the surface of water? You need to know that expired egg release a gas that we call hydrogen sulfide. Okay, hydrogen sulfide. So it's hydrogen sulfide. So in expired egg, the gas hydrogen sulfide gas as a gas, and then we all know that the density of hydrogen sulfide is equal to 1.36 kilogram per cubic meter. Okay, so what's happening is this egg here has trapped in its shell, the shell of the egg, so the gas is trapped inside of the shell. Okay, so so if I have to put, because that is a kilogram per meter cube, so if I have to put that one in the same units, that will be 1,331 kilogram per meter cube, and the water will be almost equal to 1,000 kilogram per meter cube. So let's consider our egg here having 80% of its content at fresh state, and then 20% of its content on the expired state. Okay, no, decomposed state. Okay, so what's going to happen? We all know that for something to float at the surface of water, its density need to be
lesser,
okay, than density of water. Okay, so what's happening is the density of fresh egg, which is 1031 kilogram per meter cube, is above the density of water at normal temperature. When we talk about normal temperature, we're talking about temperature between 18 degrees Celsius and 28 degrees Celsius, or 22 degrees Celsius, more or less 5 degrees Celsius. This is as per ASME, okay, American Society of Mechanical Engineers, and ISO, the European standards. Okay, so since those fresh eggs are having a density above the density of water, so they found themselves at the bottom of the tank. And then, since these ones here, what we're going to find out, they have a density lower than the one of the water, then they find themselves at the surface of water. So let's say 100%, and then 80% of it is still at good state. So the density of these ones floating will be, let's say egg expired, will be equal to 1031 multiplied by 80% divided by 100 plus 1.36 kilogram per meter cube multiplied by 20 divided by 100. This will be equal to 824.8 plus, that will give me 0.272. Okay, so the total will be equal to 825.07 kilogram per cubic meter. So we realize that this density is lower to a density of water, which is equal to 1000 kilogram per meter cube. So this is the reason why your eggs are at the surface of water. Today I've come up with something simple and factual. Okay, so I want to talk about the beauty of fluids, which is this backbone behind the applied science of hydraulics. Okay, so without wasting any time, this is what I'm having in front of me. So this is my jack. Your jack, actually, the one that you use in your car. Okay, this is your jack, and here I have two pistons. That's piston 2, and this is piston 1. As you can see, piston 1 is smaller in terms of diameter to piston 2. So let me name piston 1 diameter small d and piston 2 diameter big D. And let's put a relationship. So let's say big D equals 3 times small d. Okay, so I'm going to talk about the principle behind the fluid which is used in hydraulic. So the fluid is considered
incompressible, which of course it is. It is incompressible.
So which means if I have to apply a force here, okay, a force here, so that force there will drive a point A there, we're going to drive another point there until that force goes and moves this bigger plunger or this bigger piston out. Okay, so what happens in fluid is, if I apply a pressure there, this pressure is the same as the pressure applied there, is the same as the pressure applied there, is the same as the pressure applied there, which means then, so the pressure applied here is the same as the pressure applied there. But here is the problem. So we know that force equals to pressure times area. What does that mean? So which means if I apply a smaller force here, okay, since my area is smaller here, that force, which means if I apply, I meant a smaller pressure here, which means that pressure gonna give a small force, and then that pressure will go by this side here, it's gonna come with a bigger force. So this is force 1, this is force 2. Okay, so that's why you see, no matter how small you are, no matter how much you weigh, so when you use your jack, when you put a pressure there, no matter how small your pressure is, so when it goes, it moves your car up because of the beauty behind the stand. So what happens is you put a small pressure there, the pressure goes, that might be small, this is a bit bigger, but the force is bigger. Now, there is a catch. We're going to talk about the catch. So here, that's how it is. I'm going to talk about the force first here. So F1 equal to P, which is the diameter squared times pi over 4. We know that pi equal to 3.14157. I want to stop there. Okay, so this is force 1. Okay, and force 2 equals to the same P times the bigger D squared times pi over 4. So if I had to get the P, the pressure here, so here pressure will be equal to force 1 over times 4 over D squared times pi, and then this side here P will be equal to the same thing, force 2 over big D squared times pi. But here we know that big D equal to 3D, which means pressure here equals to 4 over 3 that squared times pi. That will be 9. And then against this will mean that P1, P is equal to the other P, so the pressure is equal to the other pressure. And at the end of the day, because I don't have enough space here, at the end of the day, so force 2 will be equal to 9 force 1, because that's 3 squared equals to 9. So if you have to simplify there, you're going to realize that's going to remain with 9. So that 9 there, so F2 equal to F1 times 9. So if you put 10 Newton here as your pressure there, that side there, you get it 90 Newton. Wow, 90 Newton. But now here's the problem. Here's the problem. So for you to move this one here, this bigger plunger with a certain height, to move it by a certain height, you need to go also with a certain height. This relationship goes like this. So volume of the side, so V1 volumes times force 1 equals to V2 times force 2. So which means if you have to move this one here by H, bigger H, so this side here you need to go by H, which gonna be, you need to go by bigger, so you need to go more there for you to move this one higher. That's why when you are moving your car up by using the jack, you go the first time down, you go up again, the second time you go up again. So the volume, because the more you're going up and down, you are trying to put that's H1 plus H2 plus H3 and so, which is going to make a certain amount of H total, which is H1 plus H2 plus whatever times that you went up and down, and then this time this one here multiply by the force that you are putting, times the area, and then you get the result. Your car is up because the principle is clear, everything is there. As I said, the only catch is the volume, so you need to go to make sure that you go more in You go more in for you to see the other side to go up. That is what is used in jack. That's what is used in press machines. That's what is used in hydraulic stuff. So your plunger is smaller this side. Outcome. So your income is smaller this side, but your outcome that side is bigger because of the diameter, because of the. So as I said, so let me now give an example of numbers. I'll just give you an example of numbers. I say that I'm not going to give an example of numbers, but it's better to come up with numbers so that everything can be clear. So here we go. So let's say, as I said, my force here, my force there is 10 Newton. So if my force here is 10 Newton, then I'm expecting to have an outcome this side. So this is what's going to happen. So which means I'm going to give also the size of my plunger. So let's say my small piston has a dimension of 0.1 meter or 100 millimeter. Okay, so this is what is going to happen. So the pressure will be equal to 10 Newton divided by pi times d squared over 4. So that's 4 goes up to be that times that, and this one here, what gives me, so I'm having the 1273.2 Newton per meter squared. So that side, this is for this side, the pressure is the same though. So now I need to calculate the force here. I have the pressure, so we all know that force again equal to pressure times the area. Okay, so pressure times the area. So now what I'm gonna have is I have that, okay, times, I said big D is 3 times small d. So times 3. So knowing that our small diameter is 0.1 meter, so 3 times 0.1 meter, that's squared times pi over 4. So what am I getting here? So I'm having 0.07068 times 1073.2, this times 1. So this equal to 89.9972 Newton. So that one there is actually 90 Newton, as it was said. Okay, 90 Newton. So this is just what I said. Today we want to know why the boats or objects of the kind, okay, do not sink into water beside their weight, beside their mass. And behind us is hidden the principle of Archimedes, which stated that for any object immersed in water, this object undergoes a force, okay, a vertical force, which is applied
upward on the object,
okay, against the object, which force is equal to the water displaced or to the liquid displaced by this object which is found in the liquid. Right, so here we're having our boat, which is right now is in the sea. Okay, and we all know that the volumic or the mass volumic of the seawater, because of the salt that is involved, is equal to 1025 kilogram
per cubic meter. Okay,
right. And realize that this boat, once it finds itself in the water or in the sea, it displaced a volume of 80 meter cube of water. So this says it means that the mass that is being displaced by our boat is equal to 80 meter cube multiplied by 1025 kilogram over meter cube. That means that and that will simplify themselves, and this will be equal to 82,000 kilogram. This said, knowing that our acceleration of gravitation is equal to 10 meter per second square, it means then that our force, which is equal to the mass times g, which is the gravitational acceleration, this is equal to 820,000 Newton. 820,000 Newton. That's what it says there. So now, knowing that our boat has a mass of 15 ton, which is equal to 15,000 kilogram. And then now, which means that the force of our boat, which is applied on the water, remember, so the weight of our boat is applied as a force on the water, and the water applied according to the Archimedes principle, which we call the buoyancy force. This is the buoyancy force. Okay, applied a force of buoyancy, which is equal to the displaced water. So the displaced water, which is 820,000 Newton. So here, this is the force of water applied on the boat, right there, and this is the force of the boat applied on the water, which is equal to 15,000 kilogram multiplied by the gravitational acceleration, which is 10 meter per second square. And this gives me 150,000 Newton. We realize that this one is lower than that. So since the force of the boat, our boat is big B, and that is the buoyancy force, which is, I can call it now, is the force of water, or buoyancy force, is lesser than the force of water. So that's why our boat does not sink. The reason why some objects, even though small, they sink because the displaced water, or the displaced liquid, is lesser than their weight. That's why they sink. That's why you see, if you put a ball, let's say a marble ball, in water, it sinks. Why? Because its weight, the weight of the marble, is higher than the weight of the displaced water. So here for you, I have this guy here. His name is J. So J goes into the pool. So this is what happened. So when J realizes is in the pool, the water, okay, let's say our water was at that level, H. So we have, once J realizes is in the pool, we have a certain J, second J prime. So that day, I'm going to put here, that day, okay, multiplied by the width of our pool, multiplied by the length of our pool, this is equal to the volume of J. And for record, you should know the mass volume of a normal human being, or the average of an adult is human is 1062 kilogram per mass cube. So this is how you can get J weight by multiplying the volume of the water displaced by that volume. Let's put it like that for you. That mass volume. So it was a pleasure of mine sharing this with you, and I hope that you guys enjoyed it. And remember, if you haven't subscribed, please subscribe. And if you feel like sharing this, please share so that other people might know what you know. And remember to tell other people what you just receive as knowledge or something like that. And I hope that you're gonna take care of yourself, and I hope to see you for the next video. For now, I'm gonna say bye.